Okay, so before I go through this derivation and try to do what I asked you guys to do, I just want to talk a little bit first about flow in the vertical direction. Because flow in the vertical direction, we can't really use the pressure-based form of Darcy's equation. And you'll see why here in a second. Because if we take a static column of fluid, could be 3 meters, the thickness of the formation, doesn't matter. The pressure at the bottom of the formation is going to be higher than the pressure at the top of the formation, right? Let's say that this is our interval H of the rock that we're producing from. So the pressure at the bottom is going to be greater than the pressure at the top. Okay? And if we use the pressure-driven equation for velocity, it would suggest that fluid is going to flow from the bottom of the reservoir to the top of the reservoir. All right? Like in a swimming pool. Okay? But the water at the bottom of the swimming pool doesn't flow upwards. Right? Not that Darcy's law applies, but if you filled your swimming pool with sand, then you would have Darcy's law applying. And still, the water at the bottom would not flow upwards. Do we agree? It's a static column. By static, we mean that the velocity, what we mean by static column is that the velocity in the z direction is zero. There is no mass transport. There's no movement. And to guarantee that, we have the static column differential equation, which says that pressure is a function of distance in the z direction, in the vertical direction, is equal to the density times the acceleration due to gravity. Okay? And if you solve that, you get pressure is a function. If we solve it, if we know one pressure at one point, then we can have the reference pressure plus rho g and then z minus reference. See? I think that's right. Okay? Where z is increasing, going downwards. You have to be careful of the signs. So that's the equation for pressure here. So how do we guarantee this? Well, we guarantee this by using a form of the Darcy equation, which is using the pressure gravity potential. Okay? The pressure gravity potential, phi, which is basically pressure plus rho g, and of course it's z, if you will. Okay? Or typically in reservoir simulation, which this is where it's only used and for practical purposes, there's going to be some reference pressure at a reference depth specified in the input data set to your reservoir simulation model, so that you can come up with this specific, this form. Like that. And that potential, if we plot the potential here, given by that, then basically that potential would look like this. Okay. That's the plot of potential. This is the plot of pressure. And the derivative of that potential with z is 0, so we don't get any flux. Okay? So that's Darcy's law in the z direction. Okay, so that So now let's derive the oil rate equation. QO. Now, because when I use rate, I'm always going to talk about surface rates, okay? And if I talk about rates down in the reservoir, I'm going to write OR, capital R for reservoir, okay? So I'm just going to simplify now like this, okay? Surface oil rate. So the first question is, we've got this equation for our radial cylindrical geometry, right? This is for radial cylindrical geometry. That was what I asked you to do, okay? So in the radial direction, if you will, it's K over mu dP dr. So that should have been the first thing you did, is you did a coordinate translation, okay, from x to radial. That was the first thing you needed to do. Now the next question is that we basically said that Q oil reservoir, which is Q mass of the oil, this is the mass rate, okay, that's, probably can't read it. Okay, that's the mass rate of oil. This is oil rate at reservoir conditions, so this is at pressure in the reservoir, which is a function of radius. It's also a function of z, which I'm not going to integrate. What I should do is integrate from top to bottom, and you'll see that you get the same rate equation at the top and the bottom, but you'll basically, we're going to assume that it's primarily or only a function of radius. So it's the mass rate times, let's see, that would be divided by the density of the oil, right? That would give us volume. And it's the mass rate that we're basically, steady state consists of the mass rate of oil being everywhere in the reservoir. I should probably drop the z, is going to be constant. That's what we mean by this steady state condition. And I'm just going to ignore the z component, which I just talked about and said you couldn't ignore. But I said you couldn't ignore it when you talk about flow in the vertical direction. If we just flow in the horizontal direction, then the fact that the pressure is higher at the bottom than at the top, it doesn't have any influence on radial flow direction. I'm not going to prove that. So, not quite sure why. Okay. Now, if we've got the velocity as a function of radius here from the differential of the Darcy equation, how do we calculate the volumetric flux at any radius? How do we do that? Okay, what we want to know, what is the volumetric rate at some radius? What would that be equal to? Well, that would be equal to the velocity, right, at that radius, times what? There's lots of areas. Let's just look at the area here. We've got, now we're looking at this radius out here. Okay, it's the area proportional to the velocity vector. That gives us volume. Okay, otherwise it's meaningless. I mean, you can't pick any area. So it's the area. Is the area proportional to flow, which, I'm sorry, perpendicular is the word I'm looking for, at the given radius. That's what you need. That gives you the volume. Do we agree? So at the RE or at the RW or any R in between, should be a valid equation. So that's kind of the second step. What is the area perpendicular to flow? 2 pi r. There we go. We need an extra dimension, h. Okay? So that's the area perpendicular to flow at the radius r. So here we're going to use our Darcy equation here. This is just a simple transformation using the area. And then what we want is the surface oil rate, which I'm just going to call QO. We want it in stock tank $40 barrel oil rates. Not something that's 10% higher down in the reservoir that nobody's going to pay us $40 for. That's cheating. Okay? They meter it at standard conditions. They pay $40 for a metered stock tank oil rate, and that's what we want to use. So what's the relationship between QO and QOR, which we have? We have an equation for QOR. So let's go back to our PVT part of the course. And we've got oil formation volume factor is defined as an oil volume at, for example, if it's a reservoir BO at some pressure in the reservoir and temperature, of course, over, if we take that reservoir volume to the surface through the process I gave you, then we get a certain $40 sellable oil. But if you talk about volumes or volumes per day, it's the same thing, right? So that's QO. That's the same as QO, just divide by 1 over delta T, 1 over delta T. And we've got QOR over QO, like that. Okay? And we said in the beginning of the problem, I said, what was BO? I said 2 things about BO for this problem. The magnitude was 1.1, and that approximately we could say it was constant from 100 bar to 20 bar. That's what I said. So approximately 1.1 constant. Okay. So what we can do is we can write QO is equal to QOR 1 over BO, right? But what's QOR? That we got up here. Put the Darcy equation in there. K over mu O dP dr. that's the velocity term, times 2 pi RH. That's this cross-sectional area. And then 1 over BO. Okay? So we're getting closer because this is what Curtis wants. That's not what I want. It's your well, you want it. You want to know how many barrels per day you're going to be making. So whether you have to get a job or you can just kind of relax and have the good life. Okay? As long as the price is $40 a barrel. We've made the assumption, for the sake of this problem, that mu O is approximately constant. It was about 0.5 centipoise. And VO is approximately constant, 1.1 cubic meters per standard cubic meter, or barrels per stock tank barrel, whatever you want to use. So what else? H is constant. So let's collect all the constants together. So constant K and H, we're going to assume that K and H constant. Two pi, that's constant. KH, we've got mu O BO, constant. And then what else? R dPdr, is that right? Is that everything? Yeah. Now, steady state assumption says that, at least Curtis says that that's the assumption, is that Q oil mass is constant at all R, all radius, but that means that QO reservoir is constant there because that's just simply equal to mass divided by the density, which is constant. And because the translation of QOR to Q surface oil, $40 oil, that's also a constant 1.1. That also means that the flowing surface oil, if we look at that, that's also constant at all R. So we've got this equation up here, and the QO barrels, stock tank barrels per day, is independent of radius. Because if it was dependent on the radius, then we would have to include it inside the integral, the radial integral, the integral on the left-hand side, which we haven't done anything yet. So basically, we're going to bring dr, everything with radius to do on the left side. You got 1 over r dr. We've got the QO here, but that's a constant. So when we integrate this, we can take it on the outside. We take it on the outside because steady state assumptions have been made. And this is what steady state assumption means. That's going to be equal to our constant 2 pi kh mu O BO integral dP. Okay? This is a constant. Approximately constant. I'm going to call it omega. I'll use it later in other connections. It's a constant that has the KH. It's got some PVT. We will also include unit conversions in that eventually, because right now we're assuming pure SI. We're assuming that there are no unit conversions. We haven't talked about units yet, but this whole thing here will actually, what I'm going to do is I'm going to do it like this. KH will always pull out. But this term here, the 2 pi has to do with being a radial cylindrical geometry. We could change that. The mu OBO, if it was a gas or water or something, it could be different. So I'm going to call this part constant and then put the KH. It's also constant out here. Okay? Now, when we integrate this, we have to integrate it from the well bore out to the external radius, right? So from RW to RE. And the pressure at the well bore we call PWF. We already discussed that on Tuesday. It's just what we call it. We don't call it PW because the well might get shut in sometime. We have a different term for that. So we're going to call it PWF. And the pressure at the outer boundary, we call it PE, external boundary pressure. Okay. And everybody remembers the integral of 1 over r. So you've got QO log RERW, okay, is equal to this 2 pi mu OBO KH PE minus PWF. Okay. So then we can write the final equation as 2 pi That's what I was hoping you would get to. Okay? That entire term there is called the productivity index. Okay? The productivity index is the name that the president of Schlumberger remembers from his course here. It is the term that's used the rest of your career, no matter what you become. And he's not an engineer anymore. He's the boss. But he remembers, you ask him productivity index, he'll tell you immediately what it is. You ask him about the formation volume factor, he might be able to give you a little explanation. He says it's needed, it's important, but maybe not. But the productivity index, he'll know. Margaret Övrum, the highest vice president, I think, in Statoil, she knows what a productivity index is. Okay? It's called the productivity index. Okay? That whole term here. And its unit is stock take barrels per day, read times $40 per barrel. That's why these people know it. That's why presidents and vice presidents know the number. Per PSI. Per drawdown. And this term here is called the drawdown. And the drawdown is also a term that the very, very highest level, even the drilling engineers, as I usually say, probably even the geologists, know what drawdown is, and they know what productivity index is, or they think they. The geologists say they think they know. The presidents and vice presidents, they know. Okay? Unit PSI. At least those are the conventional units. And convention, there's different conventions, but sometimes they write it PI. But I think in the SPE, the term capital J is used for productivity index for some reason. I'm not sure. Okay, but we'll just usually write PI or call it productivity index, but that's what that is. The last paper that's standing, most standing, the PVT kind of god of okay, of our industry. The last paper he wrote was about this rate equation, productivity index. Okay, just as an anecdote. Okay. Now, is there anything that hopefully you'll see. You knew all this stuff, right? None of what I went through here was a surprise. Maybe the steady state assumption. The assumption that the mass rate is the same everywhere. That's what you have to have a so-called steady state system. Basically, it's saying that what goes in goes out. That's another way to say steady state. Okay? And if what goes in goes out, it says that basically we're not accumulating anything in between, so that what goes in goes out. If you take the derivative of that with respect to time, that's the rate. The rate, it has to be the same everywhere where it's flowing. And here it's flowing at the external boundary. Why is it flowing there? Because the pressure is constant. The only way to keep the pressure constant is if something's flowing in there. Now, it doesn't happen very often that we have stuff flowing into our drainage area, but just for the sake of the development. So the steady state assumption of what goes in comes out, that's fundamental. Pipe flow, and in this case, reservoir flow. So that might not have been completely clear that this is what the implication of that is, that the stock tank barrels per day flowing anywhere in this volume is the same. Okay? Now, this is what should have been taught when you heard about Darcy originally. Okay? Because this gets you to probably you just ended up seeing the equation QO is equal to PI delta P. And of course, you will remember that equation. That is so fundamental. It is like PV is equal to NRTZ. You have to remember it because you want to tell your kids and grandkids that you were an engineer at one point. Okay? It's something to be proud of. This is one of the equations that you have to learn as a petroleum engineer. But how you get it, it's kind of nice, warm and fuzzy feeling that you feel like, now I know where we came up with it from. There's no magical tricks going on to get there. Okay? Even Curtis could derive it, and I was never that good in math. But it's piecing together stuff like this. Converting velocity to volumetric rate, you have to remember back that, that's perpendicular to flow. We know that we're selling these barrels, not these barrels. Okay? Things like that. It's just you have to know that. So hopefully you feel comfortable. If I remember to put this on the exam, you can do the derivation. Okay? The problem is I can't give it on the exam. Why? Because I let you take the book in. And you can write the derivations in the book. So that's why I don't give derivations. But hopefully you would be able to do it even without the book, because there's nothing really special to get there. But it is really an equation that is very important. Everybody knows it in this department. I think even the geophysicists teaching know this equation, I hope. Pays their salary. All right, so we'll take a break and then we'll come back and talk about gas.